Good morning, students. So today we will discuss the first chapter of fifth sem organic chemistry, that is NMR spectroscopy. Before we move on to the NMR spectroscopy, we must go through some basic concepts in the spectroscopy. First, what is spectroscopy? In general, spectroscopy involves the study of interaction of radiation with matter. When we say radiation, we basically mean the electromagnetic radiation, which is called a light, like sunlight. Sunlight consists of electromagnetic radiation of different wavelengths. So when you say radiation, and we represent its energy as h nu, where h is Planck's constant and nu is frequency. Frequency is the property of wave, the number of waves per second, that refers to frequency. There are two properties of wave which we commonly use throughout this chapter. One is the frequency, that is h nu, that is nu. That's number of waves existing in 1 second. What is the frequency, in which frequency the wave is moving or propagating. Second is the wavelength, the distance between two crusts and trough, as you know. So we will commonly use these two terms throughout the chapter. So when we talk about the radiation, it means electromagnetic radiation. As you can see, electromagnetic radiation is a radiation which consists of both electric field and magnetic field. As you can see, electric field is represented by red lines, magnetic field is black lines. Both are perpendicular to each other, and both are also perpendicular to the propagation of radiation in which that wave is moving. So when this radiation having suitable frequency or energy that strike on a matter, this is any kind of matter, you can call it compound or some substance or some organic substance. Matter means some organic substance or molecules, pure substance. When we strike this light on a matter, three things are possible. First is that matter or that compound absorbs some light. Second is that matter or compound reflect light and transmit some light. And third is nothing will happen as the light passes through the matter without doing anything. When this happens, it means that matter is transparent. But most of the cases, either the light reflect or it transmits. Some part is observed by the matter. So now question is, why this matter absorb light, and when it absorb light, and which light it absorb easily? That depends upon as we already studied in the Bohr model, that there is a compound, and in compound there are atoms, and in atom we have some discrete energy level. There are some energy levels like E1, E2, E3 which have a particular amount of energy. That's known as a discrete. Discrete means that the energy, suppose this is your E1, this is your E2. So E1 is a ground state, E1 is excited, E2 is excited state. So E1, either the electron can exist in the E1 state or in the E2 state, not in between. So this is called quantization of energy, means energy is quantized. So similarly, whatever the matter is, whether it is a compound or any molecule, whatever it is, it has atoms, and atoms have these energy levels. So when the frequency of this radiation matches the gap between the two energy level, then it absorbs light. It means whether the light is absorbed by the matter or not, it totally depends upon the nature of the matter. which type of frequency this matter absorb, that totally depends upon the matter. We can use a various light with a various frequency, but which particular frequency that matter observe, that totally depends upon the nature of this matter. When the frequency of this radiation, electromagnetic radiation, that matches the energy gap between the two energy levels, it will observe. It means the nature of this material or this matter can be detected from the observed wavelength of radiation. So this is an interaction. So spectroscopy is a term which involves the study. We have to study the interaction between the radiation which we are striking on the matter and the nature, means from the frequency of this radiation we can detect about the nature of the substance. So ultimately, what is spectroscopy? When we strike light on a matter either absorb, reflect or transmit the light, and based upon that we can find out the nature of the matter. So our main aim is to find out the nature, or ultimately to find out the structure of this organic compound. So the structure of organic compound can be detected by studying the interaction between these two. When we study the interaction, we can easily find these structures. So this is about the basic concept, like what is spectroscopy. Spectroscopy term is used to find out the structure of any unknown compound, organic compound. Means its nature. So this NMR spectroscopy that give information about the how many types of hydrogen are present in the compound, this compound, how many types of carbons are there, where they link, which hydrogen are equivalent, which are not equivalent. All this we study in next lectures, coming lectures. So the basic thing is, what is spectroscopy? Is the interaction of the radiation which are striking on a matter and the matters. So from this interaction we can find out the structure of the compound. Okay, because there is one important point to keep in mind, that the absorption of this light totally and only depends upon the nature of this matter. Because every matter has a different energy gap between the two discrete energy levels. So when the energy gap that you can say matches with the wavelength of this radiation, only then the light is observed, otherwise not. It means absorption of radiation totally depends upon the nature of the material. So from this interaction we can find the structure of the matter. So this is the range of spectroscopy. So depending upon the property being studied, a specific wavelength of radiation is chosen for interaction with the matter. Means which property of the matter we want to study. Depending upon that we must choose the proper wavelength. Because when we use different radiations, like for example, let us say you are looking at the dynamic of molecule, rotation of molecule or vibration of molecule. So there are different energy involved. So this is an electromagnetic spectrum in which the various wavelengths are divided according to their frequency. The unit of frequency is hertz, that we will use throughout this chapter. Or wavelength. Wavelength is in meter, that increases from, you can see, from left to right. So this blue line shows the increase in wavelength. As wavelength is what is wavelength? Actually is the distance between two crust or two trough. Like these are the two trough, these are crust. You can see this distance that keeps on increasing. It means wavelength keeps on increasing. Simple. Iski wavelength of X-ray is lowest and wavelength of radio waves maximum. Frequency and wavelength, we know that according to this relation mu is equal to c by lambda of electromagnetic wave theory, inversely proportional to wavelength. If the wavelength increases from left to right, it means the frequency that decreases. You can see 10 is per 20 to 10 is per 4. Okay. Now, which property of the matter we want to study? that depends upon the wavelength. We must choose the proper wavelength to study the particular property of the organic compound. Because organic matter, when we radiate or when we strike a light on that matter, it responds differently. Different wavelength or of light is used to find out the different property of that matter. So, if we start with the lowest frequency, you can say the lowest frequency is that 10 is per 4. You can see is a radio wave. The wavelength is 10 is per 3 meter. So here the structure of molecule can be determined by this. This radio wave frequency radiations we will use in the NMR spectroscopy because these are suitable to find the structure at this level we want to find out. This is the rotational vibrational electronic state. You know that one electronic level, like if we have these two electronic levels and these electronic levels have, this is E0, this is E1 electronic level. Two electronic levels have a number of vibrational levels. So these are the vibrational levels, say V1, V2, V3, and between two vibrational levels there are rotational levels. So means for rotational level energy required is less. That's why wavelength required is more. Okay. Then comes vibrational, then comes rotational, then again structural. So this is just a overview of this electromagnetic spectrum, that which type of properties we want to study of the given compound. We have to choose the proper wavelength according to that property. Like in this electromagnetic spectrum, we can see that there is a radio wave having the highest frequency, or you can say lowest frequency and highest wavelength. Highest wavelength means its energy is maximum, that we will use during this NMR spectroscopy. After that, microwaves are there. Microwave, they cause rotational vibrations. So to determine the rotational energy levels or transition in rotational energy level, we will use the microwave spectroscopy. Then we have a IR spectroscopy, in which we generally study the vibrational transition and vibrational transition from ground level to another, sigma to sigma, so like that. And then we have a visible, that is for ultraviolet. These are used for electronic state, that Woodward, Fisher, Schultz, 12 lambda max of any compound. So these are used. X-rays are also used to find the structure of molecule. So for the NMR spectroscopy, we must choose a proper wavelength for the interaction. So we will use the radio wave frequency here, and because we want to study the structure at this level, that these radio waves are suitable for the study of organic compounds during NMR spectroscopy. This is the instrument setup in general for NMR spectroscopy, and this is very common for all other spectroscopy also. Some parts are common. In this instrument setup, we require a source. Source is electromagnetic radiation, and we will use a radio frequency wave as a source for NMR spectroscopy. Then there is a sample, that radio frequency waves or radio waves, they strike on a sample. Sample in case of NMR spectroscopy may be in the liquid form, gaseous form, or in the solid form. This is the advantage of NMR spectroscopy over the other. In some type of spectroscopies we can only use solid state, or we can only use liquid state, but in NMR we can use all the three states of matter. Sample may be in any state. Or in liquid state, suppose we have an organic compound which is a non-polar, we must dissolve it into some suitable solvent. About the solvent we will discuss later on. So when the light strikes on a sample, the detector detects its electronic component of the instrument. It detects the radiation which is transmitted or which is absorbed, because that sample that absorbs some radiation depending upon the energy, the state energy gap between the two energy level, and or you can say based upon the nature of the sample, or it behave towards light. All the samples, they behave towards light differently. Even all the bonds, they behave differently. So this sample absorbs some light, transmits some light, reflects some light. That detector detects all type of such radiations, and then this detector sends message to analyzer. Analyzer totally analyze all the radiations which are coming from the source and reaches to that detector. Then that analyzer sends signals to the display or recorder, and that recorder gives us the output in the form of spectrum. This is a spectra. And in general, this spectra, we will discuss later on about the detail of this spectra. Just this is the overview of instrumentation. So this is spectra which we get just like an ECG. When we do the ECG at the hospital, we get a strip of paper with this such type of lines up and down. So here we get a spectra of this type. At the end we have a small peak at delta 0, that is of TMS, tetramethyl that we will discuss why it is used and where it comes from. These are the various peaks, these like this. These are the various peaks with the different intensity. Some are more intensity, some are small intensity. That depends upon the nature or the structure of organic compound. We get various peaks. If we're doing H1 NMR, because this NMR spectroscopy that is further, we will divide it into two parts, H1 and C13. H1 is a proton NMR spectroscopy that give information about the number of protons present, and these peaks they are corresponding to the various types of proton present in the organic compound. If suppose an organic compound is there and it contains about 5 types of protons, different non-equivalent protons, so we get 5 peaks. And in C13 NMR spectroscopy, you get various types of carbons. Suppose the organic compound is there and it contains about 7 types of different carbons, non-equivalent carbons. We will get 7 peaks in C13 NMR spectroscopy. So spectra is just a group of peaks appearing on a paper. From these peaks, we will find out the structure of the organic compound by studying the peaks, peak height, peak location, where the peak is from delta 0 to delta 12, where it is. That's called a chemical shift. We will discuss later on. And from these peaks, we will find out the structure of organic compound, because we come to know from this H1 NMR spectroscopy that how many types of hydrogen are there, from C13 NMR spectroscopy that how many carbons are there. So by analyzing or by studying these spectra, we will ultimately find the exact structure of the organic compound, which is here as a sample. Okay. So this is the general instrumentation setup for NMR spectroscopy. Next, in NMR spectroscopy, we will go a little bit deep into the concept. Like this is the matter which we were used to analyze the structure of with the help of radio frequency waves. So this matter, if we further go zoom in on this matter. This matter consists of some molecules and compound, and ultimately each molecule or a compound that is made up of atom. So this is atom in which there is a nucleus and electrons are revolving around this atom in three-dimensional space. Okay. So if we zoom on the nucleus, only on nucleus, so this is your nucleus, which contains protons, black one, and neutrons, red one. You can see here this is nucleon, and collectively these protons and neutrons are called nucleon. This word is used, nucleon, here it is. So now these nucleus which have a proton and neutron for neutral atom, both the proton and neutron, they have the same number of proton and neutron. Proton has a positive charge, but neutron have no charge. It means the charge on this atom is totally dependent upon the, you can say, proton. Means nucleus, the charge on the nucleus is only because of the proton, because neutron do not have any charge. It's a neutral species. So this is proton and this is neutron, red one. Proton has a positive charge and neutron has a zero charge. Okay. And you can see that the spin value of proton and neutron is same. For proton and neutron, spin value is same. We can write here half h cross. H cross is equal to h by 2 pi. So either its spin plus half or its spin minus half, that depends upon its nature or probability. according to the spin quantum number, each electron has a spin, so this proton and neutron also have a spin. So this is a nucleon actually. Proton has a spin half h cross and neutron has a spin also half h cross. So when these proton and neutron, what happens in that when proton and neutrons pair up with each other? So there may be a two type of pairing when they pair up. Parallel pairing results in addition of spin value, and anti-parallel pairing essentially cancel out the spin of the particle. So when there is anti-parallel spin of proton and neutron, all the protons and all the neutrons, then the net spin, that is cancel out, and net spin will come out to be 0. So net spin value be 0. When any atom or any nucleus have a net spin value is 0, NMR cannot detect it. For NMR, for radio wave radiation, that substance is nothing. Cannot detect, cannot recognize it when the net spin value is 0. Net spin values become 0 only when proton and neutron, they pair up anti-parallel manner. So net spin value is always the value which you arrive at after pairing up all the proton and neutron. So for NMR spectroscopy or the compound to be detected by NMR spectroscopy, you must show that the nucleus or the atom that must have some net spin value. That net spin value may be, you can say maybe 0, maybe integral, or maybe half integral. Okay, so the net spin of the nucleus is equal to the sum total of spin of the nucleon after pairing them up. Okay, when you pair them up, what will be the net spin? That is your total net spin value. And the net spin can be 0, half integral, or the integral. Many elements in the periodic table have non-zero nucleus spin. Non-zero means not zero. It means the elements, they are active, NMR active. They react with they interact with the radiation which we are using in NMR spectroscopy. Okay. Any molecule containing such elements with the, you can say, non-zero nuclear spin, that can be studied by the NMR spectroscopy. Means any element which have a net spin value is not zero, non-zero, that can be studied by NMR spectroscopy. Okay, here this is a small table you can see here. This is just to estimate, like the estimation of the nucleus spin you can see here. Like that's based upon the, you can estimate based on this atomic number and mass number. You can also calculate the exact value, but these methods are not out of the scope. So just to see this table, atomic mass is even, atomic number is even. When the atomic mass is even, atomic number is even. Atomic mass contains both proton and neutron. Like in C12 you can see. Atomic number here is 6. Okay, and atomic number here is 8. Both are even. Mass number is 12 or 16. Both are even. So when such thing happen, it means the number of protons. How many number of protons will be there in this? 6 protons, 6 neutron. Then the net spin becomes 0. Such elements are NMR inactive. Okay, second is when the mass number, atomic mass is even, but atomic number is odd, like this is deuterium, okay, 1H7. So here you can see atomic number is 1 and 7, they are odd, but mass number is even. Here the integral, the net spin will be integral value, that is for deuterium it is 1, for 7 and 14 it is 1. Next is, if the mass number is odd, atomic mass is odd and atomic number is even. So these are the examples. Half integral, like we have a carbon 6, atomic number is 6, atomic number is even, but mass number is 13. You can see mass number is odd, so its spin, net spin value is half. This is C13, and C13 NMR is well known for the structure determination of novel organic compounds. Again we have a oxygen, 8, mass number is okay, atomic mass is odd, 17, but atomic number is even, 8. It's also have half integral. Last is, if both are odd, atomic mass and atomic number both are odd, that is proton. This is H1 NMR spectroscopy. So based upon this, there is a H1 NMR spectroscopy, that is also known as proton nuclear magnetic resonance spectroscopy. And based upon this, you can see there is C13 NMR spectroscopy. So C13 nuclear magnetic resonance spectroscopy. So these two types of spectroscopies are well known to find the structure of organic compound. First, that proton NMR give information about the number of protons in the molecule. Second, C13 give the information about the number of carbon atoms in the molecule. That we will study in this chapter. We will study in this chapter in the next lectures. Okay. So this is up to the estimation of nuclear spin, that this is, you can say, the basic condition, like which type of elements can be NMR active, in which the net spin that is non-zero. If the net spin is zero, what is the net spin? Means the total spin of protons and neutrons, that some, when they pair up, there must be some net spin. If there is a net spin, then that is NMR active, otherwise that is NMR inactive. Commonly studied nuclei. So these are the some nuclei which are commonly studied in NMR spectroscopy. And out of these H1, C13 and F19, these are very common. H1 and C13 are generally used to find the structure of some novel organic compound, because both in combined give information about the number of carbon and types of carbon atom and types of hydrogen atom in the organic compound. And by analyzing the NMR spectra, that H1 NMR spectra and C13 NMR spectra, we can find the structure of the organic compound. 31 phosphorus, 15 nitrogen are generally used to find the structure of some biomolecules like protein, etc. F19 is generally used to analyze the pharmaceutical drugs, because most of the pharmaceutical drugs have a fluorine in it, so that's why these are silicon also, these are used to find the structure. So generally for any novel organic compound we use H1, C13 and little bit F19 also. But one common thing in all these is that they all have a spin, net spin is half. So that's why they are NMR sensitive, very sensitive. Next is about the spin and 1/3 term. There are actually 3 terms in this, you can say, NMR spectroscopy. One is a nuclear, means nucleus. We studied nucleus, what is there in nucleus, proton and neutron having a spin. Magnetic. Now we will introduce magnetic. Magnetic means we will introduce magnetic field also. So resonance, then does this nucleus become resonance with magnetic field, then only that compound, that instrument gives some spectra or NMR signal or peak. See how it happens. So we have a proton and neutron inside the nucleus with a spin half. This your spinning proton or neutron is spinning in this direction like this. Any spinning charged particle, means any particle having some charge, and this spinning, that creates its own magnetic field. It creates its own magnetic field. So each proton, so suppose we took a 1 drop of water, it contains millions of protons and neutrons also. So each proton and neutron, suppose we took a water and it has millions of protons and neutrons, each proton and neutron is just like this, is spinning. And it is, when it is spin, it creates its own magnetic field. So that behave, all the protons and neutrons, they behave like a, you can say, tiny bar magnet. Is a small tiny bar magnet, and that is represented by an arrow. That's why we generally put electron, we generally put a symbol for electron is arrow. You remember while filling the orbital, you just put like this, So what are these arrows? These arrows are electrons. You never put here EE is EE. You put just arrow. Why arrow? Because electron is represented by an arrow. So what is arrow? Arrow is a represent the magnetic field. It is a vector quantity. It is a direction and magnitude. So in a sample, in a matter which we have already studied, we have a large number of such bar magnets. In the absence of external magnetic field, they are randomly distributed in all directions, this direction, like this. But when we apply external magnetic field, they align. This is the direction of external magnetic field, upward. They align in two ways. Why they align in two ways, we will discuss shortly. So they align in two ways, some in the same direction of external magnetic field and some in opposite direction. So which align in the same direction as that of the external magnetic field, that get a plus half spin, and that's known as an alpha state. We designate it's an alpha state. And those which out of these which align opposite direction to that of external magnetic field, that is minus half, that's the value of I, and spin, and that is known as a beta state. Now we created a two state, alpha state and beta state. Green one is alpha state, red one is beta state. And there is a difference between these two. That difference is a delta E. Now what is resonance? Listen carefully. We have a magnetic field which is variable. This is the special character of NMR spectroscopy, that we will use the fixed wavelength, radio wave, and variable external magnetic field. This difference in these two levels, that depends upon the strength of external magnetic field. If the strength of external magnetic field is more, the difference will increase like this. If the strength of external magnetic field is less, the difference becomes less. Means we can adjust the alpha and beta level according to by adjusting the external magnetic field strength. So, and we simultaneously we follow radio wave light. We strike a radio wave light on a matter. Now, what is matter? Now, this is our matter having a two state, alpha and beta. Simultaneously, we are following a light, and simultaneously we are applying external magnetic field. When this wavelength of this light become resonance means the gap between these two become corresponding to the wavelength of incident light, then the one electron or that bar magnet that jumps from alpha to beta, that is known as a flipping of proton. That is known as a flipping of proton. Unless and until flipping does not take place, the NMR spectra will not form. Okay, so when the flipping takes place, when the wavelength of the incident light, radio wave, that matches the difference between alpha and beta. And this is in our hand, the distance between alpha and beta is in our hand, we can increase or decrease it accordingly. So by adjusting the external magnetic field, when the external magnetic field is more, the difference becomes more, when it is less, the difference becomes less. So by adjusting the external magnetic field, we make the incident radiation in resonance with this transition. That's why the word is there, nuclear magnetic resonance. Okay, otherwise if we do not adjust, like difference is delta T and this is not matches with the wavelength of radio wave, then the flipping will not take place, and if the flipping is not take place, you know there will be no NMR spectra. So to get the NMR spectra, to get some peak, there must be a flip. And for flipping, this distance between the two, that must be in resonance with the wavelength, because we can't change the wavelength of incident light. That is fixed. In our hand is that we can change the external magnetic field. So we change the external magnetic field in such a way that that transition become in resonance with the incident light. When this thing happens, the flipping take place. And when flipping take place, we get one peak in NMR spectra. Again, we get another flip, we get another peak. Like this, in an organic compound, when it scans from one side to another, from a low magnetic field to a high magnetic field, like, you know, some transitions are there which are possible at low magnetic field strength, and some transitions are there which are possible only at higher magnetic field strength. So when we just start from a lower magnetic field to higher magnetic field and scan the compound, we get a different transitions at different level of magnetic field strength, and we get a different peak in the electromagnetic spectrum, NMR spectrum. So that's all about this simple, this word, what is the meaning of this word, nuclear magnetic resonance. So much more in next lectures. Thank you.